Okay, can you hear me? Please, I'm so sorry. I just hope the remaining 10 to 12 minutes will be fine. Uh, okay, so Frederick isotherm, limitation of Frederick isotherm. So just like Langmuir, Frederick isotherm correctly established the relationship of adsorption with pressure at lower values. That means at lower pressures as well. So Frederick, Langmuir, and if you observe that Frederick and Langmuir also did they work together. I think we saw that. Can someone scroll up? Scroll up to page um, page 11. Page 11. You scroll up to page 11, look at Fredlink and Langmill. Okay. Have you seen it? Have you seen it? Page 11.
Yes, ma'am.
Okay, so Frederick and Langmill, something common to them is their experiments were carried out at low pressures. So they assumed low pressures. You can check out the assumptions or hypothesis of Fredlink, but we've discussed the hypothesis of a Langmuir. Okay, he assumed a single layer, low pressures, um, equal surface. I think there's one other one, low pressures. Okay, so those were assumption or hypothesis of Langmuir. So we can also see here that Fredlink, page 16, I'm back on page 16. Page 16. Um, he also correctly established the relationship of adsorption. He generated his adsorption isotherms as well at low values, low pressures. Okay. No wonder himself and Langmuir found a common ground to work together. So one of the limitations is that they failed to predict adsorption capacity at high pressures. At high pressures. So if I indicate in my question, for instance, that I should suggest an adsorption process, okay, and graph the isotherm at low pressure, if I indicate within the body of the question that happens at low pressures, then you know whose isotherm to graph, right? Whether Fredlink or Langmuir. Do you get that?
Yes, ma'am.
Yeah, because they both worked at low pressures. At low pressures. So their works fail to predict adsorption capacity at higher pressures. Okay. Just trying to run through. Then we have Gibbs isotherm. Gibbs isotherm um, assumes the adsorbed molecules are free to move over the surface. Okay. I will see from the previous isotherms that we've considered, Frederick, Langmuir, Bert, um, uh, Bert, Redlich Peterson, Uninam, Todd, all these isotherms, except for Gibbs, believed that, okay, only Gibbs believed that there is movement of molecules. After they have attached to the surface of the adsorbent, they can still move and behave like a liquid film. All others believe that once the molecule is attached, it becomes stationary on the surface of the adsorbent until maybe the process of desorption or the process of regenerating your adsorbent, because if you've been doing reading on your topics, adsorbent can be regenerated. Okay, so unless when the regeneration of adsorbent is to take place, molecules don't move, okay? Or unless during the process of adsorption where you have desorption and desorption and adsorption in both direction. But what this is saying here is that the layers behave like a liquid film. So he came from another angle when he carried out his experiment, probably read, is a later scientist. Langmuir and the likes were earlier than him. So Gibbs came and saw the process of adsorption from another angle. Okay, the absorbed layers behave like a liquid film, and this makes it possible to apply the equations of classical thermodynamics. So he brought thermodynamics into adsorption. The properties which determine the free energy of the film are pressure, temperature, and the number of molecules contained, and the area available to the film. Okay, the area available to the film. So we are familiar with pressure, we discussed pressure, temperature, and number of molecules, and we have also discussed that any one of them can be kept constant in order to graph whether an isotherm, isoster, isobar, and all that. So what Gibbs is saying that describes the Gibbs free energy, okay, from your thermal. Okay, it's a function of pressure, temperature, number of molecules, and what's your A? Anybody? What's the A? What's the A?
Area.
Okay, area available to the film. If you are following, I just mentioned it. So if you are following, okay, area available to the film. Okay, so you have that equation. Okay, your DG, the GDP. So you have for your G, for your P, for your T, and for your head, number of molecules. Okay, and then you have at constant temperature and pressure, you have here with respect to your number of molecules with respect to the area. Okay, and you have this. Your mu is the free energy per molecule per chemical film, and your A is the area available to the film. Area available to the film. Area available to the film. Okay. So you have your equation 3, equation 4, see your equation 1. The breakdown is on the so the breakdown is on 2, equation 2, and you have your free energy gives with number of molecules with the area, okay, with the number of molecules and then with the area available to the film. Okay, so the summation of both, the differential of both and summation gives the total Gibbs energy, the differential and the Gibbs energy, okay? And then you have the free energy per molecule with uh, the area available to the film. That's the equation 4. Equation 4, okay? Then you have your that the two-dimensional spreading pressure. You know, it talks about the movement of the molecules which are attached to the surface of the or which has adhered to the surface of the adsorbent behaving like a film. So you have this function as the spreading pressure. The spreading pressure. So you have your total Gibbs free energy written as equation 5, equation 6, and equation 7. Equation 5, your DG describes the equation 6, and then you have your equation 7. So look at these equations. Really, you don't have to memorize them, but you can please get familiar with them, but you don't have to memorize, okay? Okay, so if the gas phase is ideal and equilibrium exists between it and the sorbed phase, okay, that's the adsorbent, okay? The molecules adsorbed already on the adsorbent and then the gas phase. So at equilibrium, what do you have? You have your equation 8, okay, at equilibrium, your mu S on solid and your mu on G, that of gas. So, so you have your equation 7, okay, you have your equation 8 at equilibrium between the gas and the adsorbate. You have your equation 8, your mu G, gas chemical potential, okay, your mu G is the gas chemical potential, and your spreading pressure. Your spreading pressure is eventually given as your AN, that's number of molecules by the number of molecules per area available to your RT temperature and your as a function of your uh, limpy differential. Okay, that's the equation 9. Equation 9. So equation 9 has the form of an adsorption isotherm since it relates the amount adsorbed to the corresponding pressure. Okay, amount adsorbed to the corresponding pressure. Okay, so that's for Gibbs. Please, are you following? Are you following? Please, I need responses.
Yes, ma'am.
Yes, ma'am.
Okay, so what is one thing that you could say about Gibbs isotherm that is not common to other isotherms? In other words, it differentiates in 1 or 2 points between Gibbs isotherm and the other isotherms.
Gives believes that molecules are mobile after adherence, while others do not.
Okay, fantastic. Okay, so not really mobile, but the adsorbed surface, behaves like a liquid film. Okay, so that's the more technical term. So it behaves like a liquid film, while others believe that there is no movement of the adsorbed molecules on the surface of the adsorbent. Um, Gibbs brought in the thermodynamic view, okay, showing that there is there's an area available to adsorption, okay, as a function of the pressure and then the gas chemical potential all coming to Gibbs isotherm. Okay, so that's fantastic. I believe you'll read more. Page 19. Page 9. I think you are familiar with page 19. That's application of adsorption, decolorizing, dyeing, removal of odor, advanced treatment of wastewater, decolorizing of sugar syrup, the crude sugar syrup, recovery and concentration of patterns is used in pharmaceutical and bio compounds from dilute suspension, bulk separation of paraffin and isoparaffin. Okay, so for gas phase adsorption, you have recovery of organic solvent vapors, dehydration of gases, removal of toxic agents and odor, okay, air separation, separating normal paraffin from isoparaffin as well, then CO2 capture for addressing climate change. So for as many of you, I asked few of you to join the pitch that the 300 levels, and they did excellently well. I learned some of you pulled out part 5. I was hoping you would be the one coordinating them, I don't know. Part 5. Please don't give me more surprises. If I ask one of you to each of one person to join a group, there's a reason for that. Okay. Anyways, well, some of you pulled out without even informing me. That's way too bad. That's way too bad. I'm sure it's something that can be discussed. That's way too bad. Anyways, so you see, one of the application of adsorption to climate change. Okay, so it could be used in reversing the adverse climate change, okay, for CO2 capture. Okay, so let's go to page, what's the last page? Okay, this is page 19. Okay, page 20, we've discussed page 20. Yeah, we've discussed that already. So page 21, you have an exercise here. There is an exercise whereby you need to plot. You need to plot. So I want you to, between now and next week, you should lay your hands on these exercises. The exercise 1, the exercise and the exercise 1. That's the one on page 21 and 25. The one on page 21 and 25. Okay, so for the one on page 21, you have develop an expression relating the specific surface area SG with some of the adsorbent characteristics such as adsorbent size, density, porosity, and distribution. Okay. So you have here I want you to look up these equations. I have you to go through Richardson and Colton. I don't think any of you have. I think chapter 17 or so, chapter 17, where you have adsorption. Please go through it. You will find all these equations. You will find them there. I can't write all of them out, okay? So, but this is the equation for an adsorbent particle diameter, okay? For 1 gram of mass, okay, of molecules, you have this. You have this equation. So, okay. So I'll quickly go through this, then I'll leave you for today. So if you check out, you see this equation on page 21. For a single particle, its external surface area is pi d square. The particle porosity is that's like epsilon p. The total pore volume is pi over 6 the p cube with your epsilon p. Okay. The interior surface area is estimated as follows. So consider a single pellet of diameter dp, assuming that pores are of a cylindrical shape with identical diameter of pore and total length L. So what is this saying? We are trying to develop an expression relating the specific surface area, SG, with some adsorbent characteristics. Before you can choose your adsorbent, you have to consider things like, or parameters like the adsorbent size, the density, the porosity, the distribution of the adsorbent, all very important before you can choose your adsorbent. Okay, so here we are trying to relate all these properties to the specific surface area SG. Okay, so you have, if you go to page 22, your internal area. Okay, so before that, you have, assuming that the pores of the a cylindrical shape with internal diameter of the pore and total length L, then you have this. Please try to number the equations. You have the first equation on page 22. Your internal surface area is given as the next equation. That's pi multiplied by the diameter of the pore multiplied by the L. That's the length of a single adsorbent. Length of a single adsorbent. Okay. I wish we could go to the lab so that you see this adsorbent. You see a physical adsorbent. You see it. Some are like cylindrical shape, quite small, although they come in different sizes from the illustration I showed on the slide. So they can come in different sizes. Okay, so for some that are like in a cylindrical shape and have an internal diameter, so that's what we are considering here. You have the internal surface area being calculated, but pi multiplied by diameter of the pore multiplied by the length of the adsorbent. So you have this. Then the total surface area is given by this square multiplied by 2 pi over 3. Your diameter, your pore diameter squared. The p squared. I think this is okay. Your dp squared, okay, divided by diameter of pore, then your epsilon p. Just a minute, please. Okay, so your total surface area is given by this. Your total surface area, and then you have the final expression by crossing some few things out. You have a final expression here, and then the specific surface area is given as your SG. The final expression multiplied by the initial expression you have on page 21. On page 21, that's 6 over rho p multiplied by 1 over pi dq p. That's the diameter of your pore q. So multiplied by it. So they try to multiply. It says for an adsorbent particle diameter, the number of particles corresponding to 1 gram of mass. So the number of particles corresponding to 1 gram of mass is given on page 21. Okay, so that is multiplied by what we have as the total surface area multiplied by the total surface area. So the number of particles in 1 gram of mass multiplied by total surface area, which we have derived, gives your specific surface area. So which gives 4 epsilon p over rho p multiplied by the diameter of your pore. Okay, so to validate the preceding expression using properties of activated alumina. Properties of activated alumina. That's, for example, your epsilon P. What's epsilon P? What's your epsilon P? What does it stand for? What does your epsilon P stands for?
Particle
Particle
porosity.
Okay, the particle size, particle porosity, particle porosity. Okay, then your rho P. What does your rho P stands for? What does rho P stands for? It's on page 21.
Density.
Yeah, that's your particle density. Okay, particle density. So if you slot in, all these are for values for activated alumina. So you could have values for charcoal. You could have values for other types of adsorbents. So if you slot all these in, what do you have? You have 400 meters square per gram. So that's the specific surface area. Okay, that's the specific surface area. So try and lay your hands on it. The the rho P, that I'm going back to page 21 now. The number of particles corresponding to 1 gram of mass has been given. Okay, and then going back to page 22, we derived the total surface area. Okay, so the total surface area derived multiplied by the 1 gram particle mass, okay, gave us the specific surface area. Okay, and that's what we are asked to calculate, the specific surface area. So what we calculated now is for the activated alumina. So I could change it. I could give you for any of the adsorbents to calculate. Okay, then I'll try to give you maybe I may not give you straightforward, but just understand the steppings. Okay, I'll try to give you some of the formulas. You don't really have to memorize them, but understand it. You don't have to. If you memorize, you will forget. You may not understand the mechanism behind it. So don't bother to stress your brain really having to memorize all these long formulas. By the time you understand them, you discover that you can even write out the formulas without having to stress your brain. So understanding it is more important. So if you look at the exercise here, you have consider an adsorbent with your epsilon P. What's epsilon P? What's epsilon P?
particle porosity.
Yeah, with particle porosity of 0.5. Rho P is what? Rho P is what? I'm on page 22.
Density.
Rho P is what?
Density.
Density, yeah. Density is what? 1.25 gram per cm3. And pore of two sizes. You have the pore, we have 10A, and you have the second to be 50A. Please, this A has a, please, what's the A? Anybody?
Armstrong.
Yeah. Okay, so you have for 10 and then you have for 50. The volume fraction of these two types of pore are the same. Okay, estimate the specific surface area of the adsorbent. Estimate the specific surface area of the adsorbent. So you can lay your hands on that, right? You have the formulas illustrated already. Okay, so if you look at page, I want to release you now. Where is my page 23? Please, for those that didn't join this class has been breaking off every other minute. So I don't know if I'll be able to get the video for you. I expect everybody to be in class. Please, we are making efforts. Everyone should equally make effort to be in class. Please. Okay, so page 23 and 24. You're already familiar with that. Okay, page 23. Okay, that's the question. You have a question there. Okay, that's the question we just treated. Then okay, your page 24, you have the illustration for your bed isotherm. Okay, we are going to treat this, how this was formulated, this bed isotherm equation, how they came by this bed isotherm equation, and we are going to break it down and do some plotting and calculations on it on bed isotherm. Okay, so you see the type 1, type 2, type 3, type 4. You are familiar with these isotherms, right? If I ask you to explain any of these types, you should be able to. Anybody? Please, yes or no? I want to be sure we're on the same page. Yes or no? These isotherms on page 24, you should at least be able to say something on type 1, type 2, type 3, and type 4.
Yes, ma'am.
Okay. Yes, I want more responses, please.
Yes, ma'am.
More responses, please.
Yes, ma'am.
Please, more responses, more responses. More responses. Do I have people on this call or just 3 people listening to me?
Yes, ma'am.
Okay, okay,
Yes,
fantastic.
ma'am.
All right, thank you. Yeah, so we are going to stop there. Okay, thank you. So we are going to stop there. So I believe you understand it better than that of last week class.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. Okay.
Yes, ma'am.
All right. So please go through the page 25. Please do your plot. You see, this page 25, we are going to do a plot. As do your plot. You are going to plot and obtain the intercept. You are going to obtain the intercept. The intercept is 13,902. So do the plot, just lay your hands on it, read up your bets, and then do this plot. Okay. I would have loved us to go through bets now, but time is fast spent. I've overshoot the time. Please, I'm so sorry about that. Okay, so we'll stop here. Thank you very much. I hope any question.
Is there any assignment? You say we should plot this page 25.
Yes, now that is the assignment. Do it. I'm not asking you to submit, but make sure you do it. You are going to on your video and show me. You on your video, you show me. Yes. Each of you will show me. Because if I ask you to submit now, you may find it a bit challenging to do that. So you on your video, then you show me what you have done. Show me what you've done. Do it in your exercise notes. Do it there. Okay. Even if it is it is going to be that you're writing it out. Don't just look at it. Can you hear me?
Yes, ma'am.
Okay, so
Yes, ma'am.
don't just
Yes, ma'am.
don't just look at it. Don't just look at it on the soft copy PDF that you have. Try to lay your hands on it. Write it into your notes. By that, you will understand it better. Okay, because you're going to write it in the exam. Okay, so we'll stop here. I don't know if I'll be able to get the recording. If I'm able to make them together or get them in bits, I'll forward them to Sabata. And if not, I don't know, if there is time, I may try to do another video. But if not, please tell your colleagues that are not here to please go through the notes that I sent to you. All right. Any other question?
Yes, ma. I have a question, ma.
Yes, please.
Yeah, since you said we shouldn't memorize, like we shouldn't cram this format, we should understand it. Does that mean that we'll be given since we understand it?
Understand it first. Then I will test you to know if the next step I'm going to take. So I'm not promising you now, but go understand it. If you understand it, read and understand it, you'll be able to record the questions without having to tax your brain memorizing. Okay? Tax your brain to understand. Tax your brain to understand. Then you'll be able to write out the equations. Okay, so as exam draws closer, I will know what to do after your test. I will know what to do. Yes, any other question? Any other question, please? Okay, so in the absence of no other question, that will be all for today. So thank you very much. Enjoy your afternoon, okay? Please,
Thank you, ma.
your presentation is starting next week. I'm going to take an hour to finish up some of the few things we have left here, and then the presentation will start. Please, I can call on any group. So no group should be found lagging behind. Go have a meetings with your groups and get ready. All right? So see you all. Have a good afternoon.
Thank you, ma'am.